Video 3 is the main part of the Git workshop. It is about essential Git terms and concepts. First come preliminary notes about dimensions. They are valid in general for any version management system. The discussed key subjects then are the local repository, index, working directory, references and branches, merging and rebasing, and finally remote repositories. In general, the focus in repository context may be one of three dimensions. Directories. This means contents organized in a hierarchical file system. Branches. They represent variants of same sorts of contents. And history, which gives you the dimension of time with milestones. There are two concepts of trees that have well to be kept apart. If you need new different contents, then create new directories. But if you need to work out some new variant of existing content, create a branch. Git stores snapshots of local miniature file systems, not file-based changes. And Git always stores complete files, not differences. The key message is Git works on local repositories on the local disk, and Git has built-in integrity, as we already saw with Git objects and their SHA1 identifiers. The index or stage is your proposed next commit. There are a couple of other synonymous names for valid reasons. The index is also called the staging area, or staged files, or the cache, directory cache, or the current directory cache. The index fulfills three important purposes: prepare a commit, cache for speed optimization, and this is professional and sophisticated, as well as merge support. Important to know: if you blow away the index entirely, nothing is lost, and thus the index is a sort of temporary staging area. What has changed in the index? The command git status lists which files are staged, which files are modified, and which files are still unknown to the Git. The Git command ls-files lists all files, not only the files that have changed, within the current branch that is checked out, starting at the current working directory. And that means also within a subdirectory you will get only the files therein. You tell Git about changes that shall go into the next commit with the git command add. As a result, a blob is created or just memorized in the index if already existent. Also, the file name is memorized in the index, as well as the blob's SHA-1 hash of the corresponding blob. From now on, the file is also known to be tracked, if it wasn't before. Git commit wraps up everything of the Git index into a commit object. A tree object is created, a commit object is created, and the new child to the parent commit object is noted. Finally, the created tree object is connected to the new commit object. The index itself is a binary file. For all the blobs, it contains the full path names relative to the repository root and file permissions, as well as the hashes of the blobs. The data flow between the working directory, the index and the repository is presented in a relations diagram. In general, there is a local repository stored within a .git directory. It is complete and may be cloned. A checkout supplies files into the working directory and into the index likewise. Note: the head reference is first adjusted accordingly. There is only one head at any time, and it corresponds to the currently checked out per branch. The git command add marks files to be processed by the next commit. This concerns new, deleted and modified files in the same way. Finally, a commit brings staged files from the index into the local repository. For the data in motion, there are three types of analyzing differences. You can diff the working directory via the index, the working directory via the head, or the index via the head. There are convenience options for the output format, to omit the real diffs or to give the names only. The Git working directory holds the current checkout. When switching branches, tracked files are often changed. In contrast, untracked files are never meant with the working directory. Files within a repository have a state. They may be untracked, tracked, or staged. Stage means a new or existing other blob is registered for the next commit. If the file is modified thereafter, after the git add operation, it is still staged. So the current file contents may differ from that in the index, which will be committed the next time. And there also have been discussions when a directory is dirty. When is a working directory dirty? One definition mentions uncommitted changes. Another definition deduces dirty from files having been updated after stashing. In a summary, it is recommended to go into more details. And after all, it is found that a tree is clean if there are no changes with respect to the last commit, and there are also no changes with respect to the index. Fortunately, Git status is explicit about all of this. The relevance of the last remarks are shown at an example. Git status reports the file contributing.md both to be staged, that is to be committed, and also to be unstaged, that is not staged for commit. The explanation is the staged version will be committed, even if the file afterwards have been changed again, which therefore is then not staged for commit also. At last, a hint about the short form of Git status. Here we get all on one view. There are two flag columns, one for the index and one for unstaged modifications. References are symbolic names for commit objects. They are stored in a file somewhere in refs containing the hash of a commit object. There are different sorts of references. A tag is a constant symbol for a given commit, whereas a branch is a pointer symbol that follows new commits. Git commands could be used with the hashes itself, but references are more meaningful and easier to remember. I found an obvious and clear overview diagram for Git objects and references which you may want to study. The basic blob tree commit and tag objects, as well as all the known references. Note that the references, tag names, branch names, remotes and lightweight tags, all span different namespaces. The head is something special. It points to the branch that is currently checked out and will be the anchor or parent of the next commit. There are commands that show the contents of a head, as well as to recurse into the tree where the related head commit points to. Let's stay a moment at branches. A branch is a named pointer to a commit. The well-known checkout means just to select a branch. With the creation of a new commit, this pointer is advanced. Each commit knows its parents. The typical default and the built-in default branch are named master. In this diagram we see a line of commits with the hash values. Branch master and branch testing point to different commits, and the symbolic link head points to the current checked out branch testing. This is a typical scenario. The next subject is merging and rebasing. The delivered man pages are always the reference. The material for merging, cherry pick and rebase has been essentially taken from a good block of this subject. Input for conflicts has been found in online discussions. Merging means joining of histories. Let's start with a set of commits A, B, C and D. The feature branch and the hotfix branch have been created from the master branch, and the results of hotfix should go into the master branch. Because the destination of our merge is the master branch, we first have to check out the master to make it the current. Git merge hotfix then does the real job. It is a fast forward merge, only the pointer of master has to be adjusted, and the result is two branches hotfix and master pointing to the same commit. Now let's also merge the results of feature branch into the master. We still are on the master and directly can do a git merge feature branch. But this cannot be a fast forward merge because the different history trees. So how did Git handle this merge? The answer is Git creates a new merge commit which now has two parents. Cherry picking is another essential Git term. It takes one or more commits and replaces them on top of the current commit. If you are on commit D and you want to merge in the changes described by commit F, Git will replay just the selected changes of F, as a new commit F prime on top of the commit D. A common workflow in Git is to work on small branches and merge the results into the master branch afterwards, step by step. In the given example, this means we want the commit C to be adopted as child from commit F. For this, we need a new temporary branch based on F for committing. It can easily be created with the current branch being foo temp. We now can selectively merge in the contributions described by C and commit D, and the command for this is the cherry pick command. The temporary branch foo temp has advanced from master as expected. Finally, we want the original feature branch foo to point to the newly created commit D prime. Recall that the branch foo is nothing more than a named pointer to some commit. At the moment, the pointer foo still points to the commit D. We can assign this pointer a new value with the git reset command. Thereafter, the obsolete foo temp may be deleted. The needed commands are here. Note, another way for this last step to achieve the wanted result is by circular renaming. We could, in the first step, rename foo to foo obsolete, and then rename foo temp to foo. The name is now free again, and thereafter delete the old foo.obsolete. Then we get the same result. Now the explanation of rebase is easy. Rebase is just a shortcut for the verbose cherry picking with a single command. Note the sequence order. The first branch, the master, is the onto destination branch, where the second branch, foo, will be rebased onto. The main benefit from rebasing is a linear history, which gives us the possibility to perform a fast-forward merge, as shown with this command. Given there is a branch with valuable work, you don't ever want to be messed up. Then you may want to create a temporary branch just for merging. Think of a sandbox. If there is a conflict and you want just to take your own version for conflict resolution, then stage your own version of file and commit it. In contrast, if you prefer to continue with the other version, first check it out. Our alternative version is the second one here. Stage it and commit it. Finally, you can pump in any version of the file found anywhere, stage it and commit it. Remote repositories are addressed by URLs. They are configured with short names like origin. Remotes typically have no working directory and no index, which gives them the name bare repositories. The primary usage for bare repositories is as shared Git servers, where data is pushed to or fetched from. Bare repositories typically have the extension .git, but this is only a convention. Recall that references like branches, tags and remotes are stored in files in the refs hierarchy. In the given example, there is a local branch work. It may be referred to by various short names, which just have to be unique. For example, work heads work, refsets work. The contents of any such branch file, like work, is a Git object with a commit hash. There also are directories, remotes and origin. Remotes is for many remote repositories, and origin refers to a special remote repository. The directory name origin refers to a remote repository entry in the configuration file .git config. Origin is a directory and as such is already a short form for the remote URL. Within the directory origin are files naming branches for the remote repository, and as usual for those branches containing the hash for a commit, we also have valid short forms here. For origin head, it is assumed that the file head contains just the name master. Note that the remote master branch is configured in .git config separately. Also note that there are two master branches, one for the local and one for the remote repository, in separate namespaces. Their commit hash quite happily may differ. There are a couple of important things to know about remotes. There is a local copy of remotes, updated via fetch or pull. Local branches and mirrored branches both are local. Both branch types store commit hashes locally as SHA-1 hash. Do not assume that you only can access some remote branch with access to a remote server. That's not the case. The big difference is you can't work on a remote tracking branch directly. In contrast, you can always create a local branch based on a remote tracking branch and create new commits there. The mostly needed operations with remote tracking branches are the update with fetch or push as side effect, the merge. Recall that we have everything local with material and can merge remote things everywhere and create new local branches based on a remote tracking branch. Important data flows are shown in an overview diagram. This diagram is an extended version of the local-only variant we already have discussed. The most important fact, probably, is that the complete remote repository is locally available as a snapshot. And it is a read-only snapshot, say its contents may not be changed via commit from the index. What's about the remote snapshot? It contains remote-only elements or objects that happen to be only in the remote snapshot. There are also shared remote and local objects. That are objects, data files that are needed both locally and in the remote. And of course there are local only elements. These are Git objects in the local repository that are missing in the remote. The remote snapshot gets its data via fetch from the remote repository. And the remote repository is fed with data from the local repository via push. Note the small additional path from push to the remote snapshot. The local copy is updated also. There is no need to fetch again the data that has just been pushed. Checkout, add and commit always work only on the local repository but not with the remote snapshot. For merging in, however, this works both from remote snapshot as well within the local repository. And the merge in influences the local repository. There is a merge commit generated. It influences the index and also the working directory which holds the current branch. At last, let's have a look to available Git protocols. There are the local file system, the Git protocol with port 9148, the SSH protocol, the HTTP protocol, the HTTP protocol over the proxy, via environment variables, via git configs, and so on. That's all about Git remotes at this point. Creating a bear repository just needs the flag --bear. There is no working directory, therefore the Git treats the current directory the same way as usually the .git directory. But a few remarks may be useful. Let's look at this example. If this directory does not exist, it is created, and this is good. And normally there is also no risk to run a git init again to reinitialize an existing repository. But in case the types differ, you have already a local Git repository and reinitializes this as a bear repository. Then there may be problems. A clone of a repository is a copy, plus additionally the setup of relations. For all branches in the source repository, the destination clone will get remote tracking branches. They allow to fetch updates afterwards from the original source repository. On the destination clone, the head branch is checked out. In the config file of the destination clone, the rules for fetching branches are deposited. The refspec format has these components. There are two parts. One is the source, the remote, and the second part is the destination, the clone. Refs heads are the branches for the remote source, and refs remote's origin relate to the local destination, the snapshot copy of the remote branches. These relations made clear, the expression can be understood. The git fetch command needs the remote repository and retrieves all locally missing references and Git objects. The related local snapshot copies of the branch pointers are updated also. The mappings of references has already been explained. Only remote tracking branches are updated, but none of the local branches. And it does never change the working directory. Therefore, you can always run git fetch without any risk. There is also a little story. Without fetch, you have a stale snapshot copy of the remote. So please never forget to do a fetch first. Git pull is a shortcut. It runs git fetch and decides if the given branch is a remote tracking branch needing a merge. If so, it runs git merge. Pull may also be configured to do many things, but this may become confusing also. Therefore, serious views recommend to use fetch plus merge explicitly. One important note: Git pull will always merge into the current branch. We know this behavior already from the command merge. It goes also into the current branch. The workflow for push, precise and in short, is: you first need the branch's head reference from the remote repository. Check if this head reference from the remote repository is a direct ancestor to the branch's local head reference, the local copy of it. Then and only then all objects are put to the remote which are reachable from the local head reference, but which are missing from the remote repository, and update the locally stored mirrored remote references. If the remote head is not an ancestor, say you can't fast forward push, then the push fails. To wrap up important facts: only pushes that result in a fast forward merge are allowed. Only pushes to bare repositories are accepted. The roles of push and fetch may be swapped if needed, but anyway we need a fast forward merge in any case. Thanks for watching. Hope to see you again in video 4 for hands-on proof of concepts.